So comparing two elastic systems, we can examine the amplitude spectra that results from driving two elastic systems. So in the last example, I spoke about taking a tuning fork to a metal table or to a wood table. So the waves with variable frequency but constant amplitude will be directed at the two different systems. Each system is going to be forced to vibrate at the frequency of the applied force, but one will be better at it than the other. So we can examine the amplitudes of vibration by looking at the outputs of the elastic system. So if you look at this figure over here, you have an input, a function or a filter, and then an output. So with the input, in this example, everything is going in at the same amplitude. Then it gets shaped by the filter. And the output of the system has various amplitudes as a function of the frequencies. Now the greatest amplitude of vibration, in the top example, it's at the middle frequencies. The greatest amplitude of vibration occurs at the natural frequency of the elastic system. In figure A, the bottom panel, what's the natural frequency of the system? So where does the vibration occur at the greatest level? At 500 hertz. You see how there's the highest amplitude there? That's closest. So that would say, for example, be the natural frequency of the metal table and the natural frequency of the driving force. So the closer you are to the natural frequency of the table or whatever you're driving the force on, the greater the amplitude you're going to get. The further away you move from the natural frequency, the more filtering or the more cutting you're going to get, how the amplitude is going to decrease. So how are these two figures different? Both show evidence of diminishing amplitude for frequencies further removed from the natural frequency, but B shows it for a wider range of frequencies. So system A is more narrowly tuned than system B. That's a more broadly tuned elastic system. So the process of resonance does not change the frequency of vibration. With the principle of resonance, when a periodically vibrating force is applied to an elastic system, the elastic system will be forced to vibrate initially at the frequency of the applied force. But remember, the driving frequency that produces the greatest amplitude of vibration for the elastic system corresponds to the natural frequency of the system. That's why when we're talking about a driving force of a tuning fork, a metal table will be a better resonator than a wood table, because the metal table is closer to the natural frequency of the tuning fork. So this is in agreement with the second part of the principle of resonance. The nearer the frequency of the applied force to the natural frequency of the elastic system, the greater the resulting amplitude of vibration.